Hi, I'm Jonkers from the University of Twente. I'm within the robotics and mechatronics group, which is part of our electrical engineering department. And I've looked at carbon black doped polymers, which are used in FDM printing. So it's basically a doped polymer filament with these carbon black particles in it. Working? That should be working. So yeah, I'll first explain a little bit about the fabrication method we used, a bit about the doping. Then I'll go into my experimental setup to characterize these materials, the results, and some discussion. So we do a lot of 3D printing. We have this die-based H5 printer that can do 5 materials, currently modified to do even 6. So I can do silver ink, stuff for the sensors we print within our group. And I mostly focused on the interaction between electronics and these 3D printed conductive filaments. So one of the biggest problems you run into when you have these polymer filaments is that you, with FDM, you get these voids. So you get an anisotropy in the percolation network as well. I can quite clearly see this is quite a bad print to set an example, but you get a lot of anisotropy in your material. But it's also, if you want to make sensors, like piezoelectric, or you use the thermal expansion to get a thermal response, these voids will also affect your sensor system. So what I did is I made a bunch of samples with aligned, we call them track elements, the print lines you make. They also set up where your voids will be in between. So I printed both orientations, and I just looked at the difference basically. So the first thing I did is I put them into an oven. I annealed them at a set temperature because it's very important. These materials, after printing, we did a few studies, and for several days you will see the resistance drop of your sample. So we first did an anneal to make sure that it's settled, and then we did a few short-term exposures to see if we could characterize the thermal response of these materials. So basically, you ramp up the oven to 250 Celsius, and then you let it cool down, and you look at the response. And there I found these resistivities and thermal coefficients. And the interesting thing is the top one, the PLA material, which is kind of a stiff polymer. You can see that the temperature dependence is not really that affected by the anisotropy, but the TPU, which is flexible and has all this elastic effects in there, you can see that the anisotropy is there. And even if you vary printing settings to be even worse, which you did in a different experiment, it gets quite worse. You can really get these big voids, and then you really see the thermal expansion because your network is touching point and really vary a lot. And in terms of the resistivity, you can see that the ratio is kind of strange because the PLA, the NinjaTech, is also TPU material. These are similar in the anisotropy ratio observed, but it's also probably related to the doping of these materials. These are, from what I could tell from the data sheets, they're similar doping percentage because that's very important for these materials, whereas this material probably uses a different particle size, which so it's an effect on, you can get a higher conductive material if you change the particle size, which is carbon black. In the end, I realized that for the carbon black dope filaments, I could get, at least the commercial ones I tested, I could get a resistivity of 3.5 to 10 ohms per centimeter, which is, for our sensor, it's good. It's good enough to make a straight sensor that you can read out with typical microcontrollers. The thermal response matches quite well to what others found in literature, and it was also kind of predictable. And the anisotropy, at least for the thermal effects, was much less than the resistive anisotropy, which is kind of nice if you want to make the temperature sensor. It doesn't really matter how you orient your print. So that was what I did. And future work will be looking at printing temperatures, extrusion multiplier, because if you over extrude your material, you press in these voids, and in theory you should be able to get a more high isotropic material, and also the annealing, because the annealing is very important for the diffusion of these particles in your material. So it has a big effect, but I'm not a materials scientist in this respect. Within our group, we're trying to kind of keep away from that because we mostly want to build sensors and not get into the materials that much. If we get something commercial that works and we know it's reliable, then we know. So, thank you.